All right, now we can get started. There are three main things I want to do today. I want to talk about speciation. I want to talk about the niche. And I also want to talk about tolerance limits and diversity. So the niche and tolerance, and then diversity. So those are the three things on tap for today. Appreciate the fact that you guys are here. I didn't expect anybody would show up. I figured I'd be giving this lecture to an empty room. So you are to be commended for, while the rest of the university, everybody else has the day off, everybody else is barbecuing and hanging out with family and all that stuff. You guys are hardcore, you're here, awesome, that's good. Okay, one more point before we get started. From the lab last week when we were out there measuring tree heights, I have all of that data into a Excel spreadsheet. I will put that up on the web page. We're not done with that because whereas some of you have just absolutely perfect penmanship and it's easy to read what you've done and the numbers that you have make sense, others, the units that you're using are sort of questionable and the penmanship is such and or the writing device used was so poor that you can't really figure out what the heck the numbers are. Fours get confused with nines, sevens and 1s get mixed up, and what these can't possibly be centimeters or whatever it happens to be. And when somebody writes 5.5 feet, does that mean 5 feet 6 inches, or does that mean 5.5 feet? Okay, so those sorts of confusions. So what we'll do is I will ask you to take your data, and I will pass that back to you the next time we meet in lab, and to rewrite those so that we can interpret it and just make sure exactly what we have. Because I've done the plot of those data, and there's a group of observations which you know can't be true. For example, a tree that has a DBH of about 3 inches and is about 400 feet tall, that probably isn't correct. So we'll have to fix those data before we move on. All right, so let's begin by talking about speciation. Well, I guess actually before we even do that, there is one other thing that we need to think about, and that's something that you guys, we've already addressed it a little bit, but it's something that you guys would have covered when you took the introductory evolution class, right, as a freshman, and that is Hardy-Weinberg Equilibrium. Do you guys remember discussions about Hardy-Weinberg Equilibrium, right? So we don't have to go through all the math and all of that sort of stuff. You remember from Hardy-Weinberg Equilibrium that is the null hypothesis against which evolution is tested, right? So a system can either be in Hardy-Weinberg Equilibrium or not. If it's in Hardy-Weinberg Equilibrium, there is no evolution. If it's not in Hardy-Weinberg Equilibrium, then the system is evolving. It's that simple. It's not a question about whether men come from monkeys or any of that sort of stuff. It's a simple statement of fact. Evolution, right, is changes in allele frequencies over time. And according to Hardy-Weinberg Equilibrium, either those allele frequencies are changing or they're not. If they're not changing over time, then you're in Hardy-Weinberg Equilibrium. If they are changing over time, you have a system that's evolving. Okay? That's all it says. What are the conditions necessary to be in Hardy-Weinberg Equilibrium? Well, the most important one is Pandectic breeding. Followed by a closed population. Closed What else? Equal survival. And equal fecundity. Well, we can go through that list, and there are a few more in there as well. We can go through that list, and first of all, we know that we don't all have equal fecundity. Some of us go through life, are going to have lots of kids, and some of us will have none, okay? Simply the way it is. Some people don't want kids, some people want kids but can't have kids, right? Some people just pop kids out left and right, and some of them make it, some of them don't, but the point is we don't all have exactly the same fecundity. We don't all produce 2 children or 3 children or whatever it happens to be. Next, we don't all have equal survival, right? We don't all live to the same age. Some of us die young, some of us die old. Our population isn't closed, it's open. We have emigration and immigration. People, well, of course, now we're not leaving the population because we can't. Nobody will take us because of COVID-19. But under normal circumstances, people would be leaving the population, going to Canada, going to Mexico, moving to Europe, wherever, right? And people are coming in, right? People are coming up from the southern border. People used to come down from the northern border. People used to come in from Europe or Asia or wherever. Now, of course, our borders are closed. And then, of course, perhaps the biggest one is Pandectic breeding. And that's Pandectic breeding is when we mate at random. So we're indiscriminate about who we mate with, and that's certainly not true for humans. The female part of the population, at least, is pretty selective, right? Females are pretty careful about who they decide to mate with. Males, not so much, right? But we don't breed at random. We're pretty specific about who we mate with. So those are all assumptions of the Hardy-Weinberg Equilibrium, and we violate each and every one of those. And for that reason alone, we know that even our species is evolving, okay? And I gave you that example in lecture where we talked about the origin of humans, right? I think we did that where we come out of Africa, right? Everybody recalls that, okay? Yeah, so clearly, if you look at the human population today, it looks fundamentally different from what it looked like 3 million years ago, okay? There has been a lot of evolutionary change in our species. We're still humans, right? We haven't changed into something else, but we're still humans, but we have evolved, and we continue to evolve. And if you were to come back in another million years and look at us, we wouldn't look like we do today. We would be very different. It's unlikely that there would be very many blonde-haired, blue-eyed people, okay? And it's unlikely that there would be as many people as dark as Fidelis Atuo, okay? So we're going to move towards something which is brown, okay? Something in the middle. And that's simply because of gene flow that's taking place between different segments of the population. Good. So let's now think a little bit about speciation, and we had already talked about one little example, and that was this idea of what happened to the kangaroo rats in California. Okay, so we had this nice central valley, and here's the California aqueduct that's coming down like that, and there's Interstate 5, which is coming down like that, dividing that population up into 2 halves, right? So when that happens, the kangaroo rats that used to live over here can no longer get over to that side, and these guys can no longer get over to that side. So we've isolated those 2 segments of the population. And since they've been isolated, they've been accumulating mutations to the point where now they can no longer mate with one another. So gene flow between the 2 groups has stopped. And that's a key to speciation, right? In order for speciation to occur, there must be some limit to gene flow. So there has to be some limit to gene flow. You understand that that's sort of a poor terminology. I'm not really talking about genes, I'm talking about alleles, okay? We all have the same genes, right? A gene is just a region on the DNA molecule. What differs between us is the information that's coded at that gene. Some of us have blue eyes, brown eyes, whatever, okay? So what matters is the alleles, okay? But we always refer to it as some limit to gene flow. So what are the things that can limit gene flow? Well, we can have geographic barriers. How do you spell barriers? With one R or two R's?
Two R's.
Two R's. I was, by the way, 5th grade spelling bee champ. It's been downhill ever since. Once I reached that milestone, I said, okay, I'm done. I can forget all this nonsense now. Okay, so geographic barriers. Well, a perfect example of a geographic barrier is the California Aqueduct or Scenic Route 5, Interstate 5. Okay, that prevents animals from moving. Anybody here ever driven through, coming out of Reno, Nevada, going up to Idaho? What is that highway? It's not an interstate, it's 385 or something like that. There are these weird things. There are these bridges that go over this busy road. So it's a 4-lane road, divided road, you know. There are these bridges that go, but there are no roads hooked up to the bridges.
For cat animals, isn't it?
Yeah, it's for wildlife. Okay, it's for pronghorn and for mule deer and elk and things of that sort. And mountain lions and bears and everything else is moving across those things. Yeah, so those are wildlife bridges. So there's this recognition amongst wildlife biologists that these roads are a geographic barrier, so they're trying to open those things up so it isn't quite as much of a barrier. And what's interesting, I saw a paper once at these meetings where this woman, what she had done was she put trail cameras up on those things and she just recorded what sorts of wildlife was using, and it was amazing. Okay, it's like a miniature freeway system for wildlife every night. All these animals are going both directions. It was kind of cool. So at any rate, a geographic barrier is an isolating mechanism. What else might limit gene flows? We have geographic barriers. What else? Okay, we have geographic barriers.
I guess inbreeding would limit gene flow. Inbreeding.
Well, inbreeding is sort of a consequence of perhaps too much gene flow, right? Along those lines, though, we can think of some other things. There are, if you think about it, there are some things there is this, it's kind of interesting, right? If you think about, we know humans better than we know any other species, so let's think about what young males and what females do. Who's more likely to leave home and move far away, a son or a daughter?
It's usually a son.
Sons, okay. Daughters generally stick close to home. Sons generally move farther away, okay? I wonder why that is. There is this other sort of interesting phenomenon, right? If you look at distance, and this is probability of not mating, but probability of marriage. Okay, if this is the zero distance right there, then the probability of marrying somebody that lives very close to you is high. But as that distance increases, it does one of those things. So you're very unlikely to marry somebody that lives a long distance away from you. Why?
You don't interact with them?
Yeah, you don't interact with them. It's unlikely that you're going to meet them. It's unlikely that you're going to get to know them. What else? Okay. How likely it is that you're going to meet some woman from Paris and marry her? What are the problems? You're just Bubba from Missouri. I mean that in the nicest possible way. You're just Bubba from Missouri, and you're going to meet some fancy-dancy hot lady from Paris, France.
Yeah, she probably wouldn't like me very much, is that right?
Yeah, well, you have this funny accent, you know, and you dress weird and all that sort of stuff, and you don't, you know, you're just not right, okay? What is that?
Culture?
It's a cultural isolation, right? So there's this cultural barrier, this cultural isolation. Well, you speak a different language, for one thing, okay? Unlikely that you're going to meet that person. You have different responses to certain things, right? Here in this country, right, you know, everybody and his kid brother has 3 AR-15s and and a couple of shotguns and, you know, all that sort of stuff. And in France, people would be shocked even by the notion of having a firearm. Okay, so there are those sorts of things. Here, you know, we're so anti-socialism and everything, and in Europe, people are pretty socialist. Okay? Well, you're socialist too. You guys understand that, right? I mean, you like the library, you like using public roads, you like the post office, you like Social Security, you like Medicare, you like all these socialist programs, okay? The university has a socialist program. You think, well, it used to be much more socialist than it is now. We've turned it into a business model, and that's why you're paying so much. But it used to be a socialist system where you went to school for basically free. I paid my annual tuition bill when I was going to school in California, annual, $190 a year is what I paid to go to school. You pay twice that for a single credit hour. Why is that? That's because, and I know we're a little bit off topic, but that's because back when Ronald Reagan was governor of California, and as things go in California, the rest of the nation follows, when he was governor of California, he said the state of California has no business financing intellectual curiosity. In the same speech, he said that the University of California, Berkeley, is nothing but a hotbed of radicals, perverts, and queers. That's what Ronald Reagan said when he was governor of California, and he became our president, okay? But it's that idea that the state shouldn't pay for intellectual curiosity, which shifted the burden from the state paying for your education to the taxpayer. And because most Republicans don't like taxes, they keep cutting taxes, the money for education has disappeared. Somebody has to pay for it, so that means you pay for it. Okay? Sucks to be you, but there it is. All right, back to what the lecture is about. Cultural isolation. What else? Temporal. Lots of animals have very specific mating seasons, okay? They mate only in the spring, or they mate only in the fall. They have very specific times of the year during which they mate, okay? What's happening with deer right now? What are they doing?
They're shedding their velvet.
Yeah, they're slowly shedding their velvet, right? So they've got these, the males have these nice racks, well, the big males have these nice racks, okay? And all that velvet, they've cut off circulation to the skin, which is on top of those antlers. So they're rubbing that skin off. And why do they need those antlers?
To fight off other males.
Yeah, so they're going to use it in male-male combat, okay, and so on. So these guys are getting buff for the lady deer. And then they're going to mate. And as soon as they're done mating, by middle of March, those antlers are going to be dropping off left and right. Okay, mating is over. They're not going to be mating for the rest of the year. They're going to be mating this fall and early winter, okay, and that's it. And then they're done. How about you guys?
Anytime.
Anytime, okay? It's fundamentally different in humans. We're the only species that has recreational sex. No other species does that. All other species, sex is strictly business. It's all about reproduction. In us, it has a different function. It's partially about reproduction, but it's also about something else too, okay? So for us, it's hard to think about temporal isolation because we can reproduce whenever. But imagine you're a little bird and you come into estrus in the early spring and everybody else is ready to mate in late spring. You've missed it, okay? So if you're migrating and you're coming up from a place where everybody should be reproducing now, but you come up and either everybody's already reproduced or they've not started yet, you're out of luck. That's reproductive isolation. You are isolated from that other group, okay? So temporal isolation. Geographic barriers, cultural barriers, temporal barriers, anything else. I'm sure we can come up with some more. What else might reduce gene flow? Anything else?
Would it also kind of fall into temporal, like age?
Ah. Yeah, so some organisms, as they get older, right, their reproductive ability changes. Let's think about reptiles. Who has greater reproductive success? Some young, buff lizard or some really old lizard?
Young one.
No, old one. How about a turtle? Some young turtle or some really old ancient turtle?
Older.
The old turtle. Why?
Mature.
What is it about the maturity that improves reproductive? So we're not talking about mammals here, we're talking about reptiles. Old reptiles have indeterminate growth. That is, the older they are, the bigger they are. If you're a female turtle, think about it. What determines your reproductive output if you're a female turtle? How much room you have inside your shell for eggs. If you're bigger, you have more room for eggs. So the bigger turtle has more room for eggs than the small, younger turtle. So her reproductive output is significantly greater than the young turtle. For reptiles, it's almost always the big animal that wins the reproductive contest. So when two animals are fighting for access to the female, the big one invariably wins. The big one is the old one. Okay? There are these lizards in the Southwest called chuckabolas. So a lizard gets to be about that big. These things are awesome. They eat plants. And what they do is they hang out on these rock piles, and when a predator comes around, they dive underneath the rocks, and they puff themselves up with air, and you can't get them out. But like a lot of lizards, they have something called tail autotomy. So the tail can pop off. And what foxes will do is they'll go in there and they'll find those guys, and they'll reach in and they'll grab the tail and yank the tail off. And then they'll eat the tail, because the lizard stores all of its energy in its tail, not like us where we put it around our belt or on our butt or something. These guys store their fat in their tail. The trick is that in these rock piles, they have a tyrant mating system. So there's a tyrant male who owns all of the females on that rock pile. There will be other males there, but they don't get to reproduce. It's only the tyrant male that gets to reproduce. And the reason he's the tyrant is because he's the biggest, baddest boy there. And he's got the biggest tail. And when the females are deciding who to mate with, they always choose the male with the biggest tail. Okay? Like elephants, they choose the male with the longest tusks. Okay? So here's this tyrant male. He's got this nice, big, fat tail. He gets 95% of all the matings that take place on that rock pile are with him. Then the fox comes along, rips his tail off. Suddenly, he's no longer top lizard. He's no longer the tyrant. Now, it's the next guy in line that gets it. Okay? He's got the same alleles he always did, but because he lost his tail, he no longer gets to mate. Until he grows the tail back, which he probably won't live long enough to end up with the biggest tail again. In humans, for the most part, right, how does that work? Are females generally attracted to males that are younger than them or older than them?
Older.
Older, to a point, right? It's unlikely that any mid-20s female is going to be attracted to some 60, 70, 80, 90-year-old male. Why? What's wrong with some 90-year-old guy? I mean, aside from the fact that he's all shriveled and bent and stuff. What's wrong with some 90-year-old guy?
Can't take care of them as well,
He can't take care of himself?
or the woman.
Why would he not be able to take care of her?
I'd
Close to death.
Huh?
Close to death.
He's close to death? We're all close to death.
He's closer.
He's close. You don't know that. You don't know that. You might die tomorrow. Okay, he might outlive all of us. There are examples, right? What was this guy? Anna, was that her name? Anna Nicole Smith? Or she's some sort of TV actress or Playboy centerfold model or something like that. This woman with the pneumatic breasts, okay? She married this, what was that guy's name? One of the Hunt brothers or something. This 90-year-old guy, she married him. She was like 21 or 22, and she marries this 90-year-old oil tycoon. He was filthy rich. He didn't last long. He died during intercourse, which is probably the way he wanted to die. I don't know, okay? But he didn't survive very long. Why would she marry a guy like that?
Money.
Yeah, pretty clear, right? It would seem pretty obvious. She claims it was true love. I have a hard time imagining some 20-something-year-old woman falling madly in love with some shriveled up, bent old guy. But she was in love with his wallet. So age, can a 90-year-old guy still produce offspring?
Yeah.
Sure. What's the problem that an old male is going to face? I'm just giving you guys a heads up so you can plan your life out here. Okay. What's the problem that the male is going to face? Just why why are women have in their minds this biological clock, right? By the time you're 30, 35, you're starting to think about having babies an awful lot. Why? What happens roughly at the age of 35?
Pause.
Menopause? No, menopause isn't going to happen until 45 or 50. You ladies don't think about that stuff yet. You got plenty of time. No worries. You're cool. What ends up happening is that the probability of birth defects starts to go up. So at the age of 35, the likelihood that you're going to produce a kid with trisomy 21 or some other genetic abnormality begins to increase rather dramatically. It's still a low probability event, but the probabilities begin to double, okay? Well, it was 0.00001%, now it's 0.0002%. It's still exceedingly small, but the probabilities are starting to increase, okay? So that by the time you're 45, you have to be pretty concerned about this. That's why we have things like amniocentesis to do these tests, genetic testing, to figure out if the fetus that you're carrying has any genetic abnormalities or not, and you can then make a decision about what the appropriate course of action should be, okay? The same thing happens to males. So that by the time you have a 90-year-old male, if you were to look at the sperm under a microscope from a 90-year-old man, you'd be going, holy shit, this is some sick-looking stuff in here. I mean, if the old guy is bent and wrinkled and crinkled and whatnot, that's what the sperm look like too. A lot of deformed-looking sperm with a lot of genetic abnormalities, okay? So the same thing befalls old males as befalls older women. So if you have some immigration for some gimpy old geezer, some 93-year-old guy moves into town, right, and he's from some weird country somewhere across the globe, and he moves in, he comes here to Cape, and he goes down to the Rude Dog pub, or 21 Taps or something, and tries to pick up some ladies, and maybe he's got a really fat wallet. It's still unlikely that he will successfully reproduce. Okay, he might give it his best shot, but it's unlikely to be successful. Okay, so possibly age we could include in there as well. What else? Well, we know one, right, and that's morphological. Okay, so we talked about that with the kangaroo rats. If the baculum on the kangaroo rat has the wrong shape, okay, it's not going to fit. So as an example, okay, lots of animals have bacula, right? Carnivores have bacula. Most primates have a baculum. Bats have a baculum. We as humans are weird in that we don't have one, but lots and lots and lots of mammals have a baculum. Okay. What else?
Like it's availability of resources. If there's no like food or water, they're not going to breed.
Yeah, but but we're talking about you're coming into an area where we're talking about something that's going to limit gene flow. So here you have a population, and here you have a population. What's going to prevent this animal from this population getting into this one and reproducing there? So if they're already there, then there should be resources there. Okay. Well, another one would be behavior. So we have all of these little customs. Anyone ever been to Germany or know any Germans? Nobody. What's this weird thing that the Germans do when they greet? They do this thing called Gießen, right? Where you stick your hand out to shake and you go like that. You just take your head and go like that, okay? The Japanese do it in extreme, you know, what do the Japanese do like that? And how far you bow is this social status thing. You know, if you're a low social status, you have to bow really far. And if you're high social status, you just bow a little bit. Okay, that whole thing. It's this really strict, sort of rigid kind of a thing. And here you are as an American, you go over to Germany and you're trying to, you know, impress people, pick up some babes or something like that. And you're not decent and everyone's going to think you're rude and crude. Okay, you don't have the social norms. That is a reproductive isolating mechanism. You're not going to get into, you know, that social system if you don't have the appropriate behaviors. Another example in birds would be songs. Okay, birds sing these songs. The song is learned. Okay, cardinals that live here have a very specific kind of a song. And if you go to Colorado or you go to the other side of Kansas, to western Kansas, and listen to the cardinals, their song is different. The basic structure of the song is still there, but the inflections are all different. So a male cardinal that's coming from here and gets blown by a tornado over to western Kansas, going to sing his little heart out and nothing's going to happen. Because that female cardinal is evaluating the males on the basis of their plumage and their songs. And if the song isn't exactly right, her little motor isn't going to be running and she's not going to mate with it. Okay? It's that simple. So in anolis lizards, if you've ever been down to Florida or Georgia or something like that, you've seen these little anolis lizards everywhere, okay, the little Carolina anoles. They have these dewlaps that stretch out from their chins. They flash those dewlaps out, they're brightly colored. When they flash those things, it's like a dance. And it has to have exactly the right moves. It has to go out exactly the right distance, at the right time, in the right pattern. It's like a drum beat, you know, with lights attached to it. And if it's not perfect, it's not going to get the motor running on the little female lizard, and she's going to ignore him. Okay? The male has to get it exactly right to turn her on and to get her interested. If he doesn't do it, it's not going to work. There are these salamanders, these plethodonted salamanders. The males do this little dance. So in salamanders, the problem is they live in the water, and yet they use internal fertilization, but they don't have an intermittent organism. So salamanders don't have a penis or anything that acts like a penis, and yet they have to get the sperm inside the female. Okay? So what they do is the male builds this little protein mound in the water, and on the top of it, he deposits a sperm packet. And then he goes and finds a female, and he does this dance for the female. And he's got to wiggle his little butt exactly right, and make the right moves, and do the little figure eight, and go around in a circle, and all that kind of stuff. He has to have the dance exactly right to convince her that it would be an awesome idea if she would park her cloaca right on top of that little protein mound and pick up that sperm packet. And if he does the dance exactly right and wiggles his butt exactly right, she'll do it. And if he doesn't, she won't. But of course that dance and that butt wiggling stuff changes geographically. So if you look at that dance here in Missouri, it's different than the dance that gets done in Arkansas. So a big flood comes along, the little salamander from Missouri gets washed down to Arkansas, and he's doing his dance right. He's perfect, but it's for salamanders up in Missouri, not for salamanders in Arkansas. And he ends up spending the rest of his life alone. Nobody will pick up his little sperm packet. He's crushed. He's geographically isolated. He's behaviorally isolated. Okay? All right, those are isolating mechanisms. Okay? So what those isolating mechanisms do is this. Let's think about our kangaroo rats. This is time on the y-axis, and this is phenotype on the x-axis. So here's this species, and the species is moving through time. And its phenotype is changing, right? Something like that, but it's going through time. And at some point there's an isolating mechanism, and the species gets divided into two. Okay? And now we have one group which is going off like this, and we have another group which is going off like this. So we now have a speciation event, whereas initially we had one species, we now have two species. And now there's another isolation event. Now we have one species which is doing that, and another one which is doing that. Okay? That's the Brownian motion model of evolution. Do you guys know what Brownian motion is? You never learned that in high school or grade school? Every atom out there has a certain amount of energy, right? Every little molecule has a certain amount of energy, and these molecules vibrate. And if you could watch a molecule underneath a microscope, you would see that it would just be vibrating all over the place. I mean, obviously you can't do that, but they vibrate all over the place. That's called Brownian motion. We depend on Brownian motion for chemical reactions to take place. Otherwise, these molecules are not going to bump into one another, and in order to react, they have to bump into one another. So this is the Brown, because they're vibrating, right? The phenotype is vibrating as they're going through time. So that's what speciation is, and that's where the isolating mechanisms are taking place, is right there at those points. Okay. So when you think about humans, who is our closest living ancestor? Who is closest to us? All right, so here's Homo sapiens. And we obviously do the same sort of thing. Who's out here? Who's this over here? Well, let's look at all the possible animals out there that could be. How do we know that we have a relative out there? All right. When we look at evolution, what we're doing is we're looking for homologies. What is a homology? You should remember that from freshman year. What's the difference between an analogy and homology? No idea? All right, a bird flies. A butterfly flies. What do they have in common?
They both fly.
Pardon?
They both fly.
They both fly. What do they use in order to fly?
Wings.
Wings. Are the wings homologous or analogous?
Analogous.
They're analogous. Okay? Similarity in structure, right, as a consequence of similar function. So analogy is similarity in structure as a result of similar function. So both wings generate lift. Wait, is that true? Do bird wings generate lift? How do bird wings generate lift? Or do they just push against the air? Come on, this is high school. This is junior high school stuff. What's the cross section of a bird wing? Like that. What's the cross section of an airplane wing? Like that. How does it generate lift? What principle is involved? When you go home tonight, your assignment, take off your mask, take a sheet of paper, not one that's stiff like this, hold it up to your mouth and blow right across the surface. What's going to happen?
It goes up.
Like that. That's called the Bernoulli Principle. So air is coming like this. There's air going across the bottom, and now air is going across the top, but it's covering a greater distance. It's covering a greater distance, but it's the same amount of air moving, and it's going to get to this point at the same time. So this air is moving fast. And what that means is that there's low pressure across the top of the wing, and that's pulling the wing up, that's creating lift. Okay? So the bird is creating lift. As the bird wing goes through the air like that, it's creating lift. And when the bird moves its wing goes down like that, okay? So the lift is going up and forward, and it's moving the bird forward. Here's the butterfly wing. It's like a sheet of cardboard. How does the butterfly fly? They do it really well.
They push it on there.
So there you are. That's what Icarus did, right? These nice big flaps. You started doing that, and you bring it down like that, you push against the air, and that gives you just a little bit of upward force. And then you have to bring the wing back up, and that pushes you down. Spend all day long doing like that, and you're going to be stuck on the ground. You're not going anywhere. Butterfly does exactly the same thing. On the front of the wing are these little irregularities. And those irregularities, when air is going over it, create turbulence. So you get a little bit of turbulence forming right there. So now when the air comes over, it has to go over the turbulence and then down like that. So the butterfly is doing exactly the same thing, even though it has a wing which is perfectly flat. It still gets the Bernoulli principle because it has turbulence at the leading edge of the wing. So butterfly wings and bird wings are analogous, similarity in structure as a result of similar function. They're both used to generate lift. But they are not homologous. Homology is similarity in structure as a result of common descent. Analogy, similarity in structure as a result of common function. Homology, similarity in structure as a result of common descent. Your pinky finger is homologous with the pinky finger of every other primate because you have a common ancestor. Okay? What is the ultimate homology in vertebrates? In all life, not just vertebrates. What homology do we share with COVID-19?
Nucleus.
They don't have a nucleus.
Oh, they don't. Oh, yeah, yeah.
DNA, or like RNA.
Well, either DNA or RNA. How is our DNA/RNA similar or different from that of a virus? What's the ultimate homology for all living forms? I mean, this is the big one. You have somebody says evolution is a hoax, evolution is fake news, whatever. Evolution is Satanism, evolution is socialism, whatever they want to say, right? How can you say that they're full of it? What homology do you know which is irrefutable? All living organisms share this homology.
All carbon-based.
Lots of things are carbon-based. My car is carbon-based. The drugs that you use are carbon-based.
The specific structure of DNA?
what is important about the structure of the DNA. It's not so much the structure of the DNA, it's something about how we're reading the DNA.
It's all the same amino acids, isn't it?
Yeah, so
Just
what?
in order.
What is it about? Yeah, so amino acids, we can make up any amino acids we want. You're close, you're circling around it. All right. How does the body know to produce methionine?
The codon, or the base pair, or no?
What's the codon that codes for methionine?
Is it a response to a stimulus?
No, what's the codon for methionine?
Is it AUG?
AUG. Adenine, uracil, guanine. Every time you have adenine, uracil, guanine, you get methionine. Makes no difference if you're a human, a chimpanzee, a horned toad, a dusky-footed salamander, a gray bat, an Indiana bat, a humpback whale, a blue whale, a gray whale, a narwhal, a beluga, a cardinal, a goldfinch, a mouse, a worm, a cockroach, Escherichia coli, or COVID-19. We all use exactly the same effing genetic code. Does it have to be AUG? Is there something magical about AUG? No. It could have been anything. It could have been, we could have used 2 letters. We could have used 4, 5, 8, 9, 20, whatever. We ended up using 3, and that's because the very first living thing on this planet, that's the code that it used. And that's how you know that all life comes from one initial living thing. That's where everything on this planet came from. So it's entirely possible that God in His infinite wisdom is up there in heaven going, I am going to fuck with these people, right? This Shiva guy, I am going to nail his ass so bad. I'm going to set this thing up so that in the year 2020, he's going to talk to a bunch of students, corrupt their innocent little minds, and give them this story, which I made up, is all fake news, but this is the way I'm going to do it, just to test you guys. I am Satan. Okay? All right. You've been warned. But that's the ultimate homology. So, who is our closest relative? Who do we have the greatest genetic similarity to? Come on. It's not hard.
I think great apes.
The great apes. Which great ape in particular?
The bonobos.
Yeah. Chimps. Chimpanzees. There are two species of chimps, right? There are 2 species of chimpanzees, okay? And those are our closest relatives. Think about it. How do chimpanzees differ from other great apes? Well, for one thing, what's so special about human females? What do we find so intriguing about human females? How do human females differ from the females of any other species that's out there? What do they do? They have permanent breasts. Once they go through puberty, they have permanent breasts. No other animal does that. A female dog doesn't walk around with breast tissue unless she's lactating. No other animal, no other mammal does that, except for human females. And chimpanzees, when they are pregnant, when they're in estrus, they develop that tissue and they have breasts, but as soon as they're done reproducing, it all disappears and goes away. It's the only other animal that does anything close to what we do. Okay? What else? What do? We have recreational sex. Okay? Chimpanzees, it turns out, although they don't copulate, have similar sorts of behaviors. Interestingly enough, bonobos practice sex. And the way they practice it, the males practice copulation with other males. So there you are thinking, oh, there must be strong natural selection against being homosexual, right? And clearly there's not strong selection against it because it's there, right? I don't think people decide to be, oh yeah, you know, I think it would be so awesome to be gay. My life would be so awesome. I don't think so, okay? And yet you look at the chimpanzees, and the males are practicing homosexual behavior as a way of learning how to reproduce. So, there it is. And here's the cool thing. Unlike the idea that you learned in church or wherever, or in Sunday school or wherever they teach you these sorts of things, the fact that we have speciation, the fact that we evolved, doesn't mean that these guys disappeared. They're still there. We haven't replaced anybody. Species don't replace other species evolutionarily in that sort of way. We coexist. We obviously have some differences, right? But we coexist. Okay? So who else is going to be on this family tree? Well, gorillas, mountain gorillas, and lowland gorillas, and who else? Who's the other great ape?
Or orangutans, right?
Orangutans. Okay? There's this wonderful film footage with Jane Goodall. She's being interviewed by somebody from National Geographic. And she's in Borneo, and she's holding this infant orangutan. And she's holding this little infant orangutan, and this little infant is trying to nurse on her. And she keeps having to push it away, pull it away, but this little thing is hungry and doesn't see Jane Goodall as anything weird or different, as, you know, as something that's not my species. She looks at Jane Goodall and says, oh yeah, another orangutan, and just wants to nurse. Isn't that cool? There's this wonderful story of George Schaller, who's the guy who wrote the book on mountain gorillas. And he's in Africa, and he comes into this clearing, and he discovers this little baby gorilla. And he picks this gorilla up, and he comes to this clearing, and he can see the troop of gorillas on the other side of this clearing. And he just stands there holding this baby. This little baby gorilla is vocalizing. And finally, this giant silverback male from across the clearing looks up, sees the baby, and sees George Schaller holding this baby. So here's this 600-pound gorilla, and these guys, they're not fat, they are buff. And this 600-pound gorilla comes running across that clearing and is going to rip George Schaller's head right off. But George Schaller knows enough about primates and primate behavior, he knows exactly what to do. So he's standing there waiting till the gorilla gets within 10 feet, and he puts his head down and he holds the baby out like that. And the male gorilla stops, picks up the baby, turns, and walks away. That behavior is the same thing the Germans are doing when they dietz, the same thing the Japanese do when they bow. What is it a sign of? When you do that, what are you doing?
Submitting.
Submitting. It's a sign of submission. When you go to the mall sometime, okay, well, not now, after the pandemic, okay, go to the mall, Friday night, all the little teenage twits are walking around the mall, you know. And there'll be a group of little teenage boys walking around. and you're bigger than they are. So just walk around and find a teenage boy and make eye contact. So walk in the opposite direction that they're going and just make eye contact. How does he respond?
Looks down.
He looks down, he looks away. He's breaking eye contact, he's looking down, he's indicating submission. Next, find some guy who is taller than you by about 6 inches and outweighs you by about 100 pounds, and is nothing but you've got these big bulging shoulders and traps and arms and stuff, and he's just this huge ass primate walking down. And just look at him straight in the eyes and watch what he does. He's not going to look down, he's not going to look away, because he outweighs you by about 100 pounds, he's got at least 6 inches on you. Just watch his hands. His hands are going to go like this. His elbows are going to bend, his arms are going to go out like that, and he's just ready to clock you. And just for grins, see how long you can continue to look at him. And there will come a point at which you're going, holy fuck, you're going to look down, you're going to wave or something like that, you're going to look away. It's going to be exceedingly difficult not to, and what happens if you don't look away? Your next memory will be the roof of the ambulance as they're taking you to the emergency room, okay? All right, so that's this behavior as well, which is homologous across these groups, okay? So the point there is that speciation doesn't result necessarily in replacement, okay? We coexist there, and we do have these close evolutionary relatives. This was a cool thing that came out of this, this mitochondrial DNA study that was done years ago trying to trace humanity. One of the cool things is that there's a significant part of the human population which has genetic information from Neanderthal man. In other words, there was mating that took place between Homo sapiens and Neanderthal man. So in the early days of Neanderthal man, we were mating with Neanderthals. Isn't that cool? All right. Let's talk now a little bit about speciation. Give me about 10 more minutes. We'll talk about diversity another time. Let me talk about niches and tolerance. And by tolerance, I don't mean, be cool, be friendly, be kind to your human travelers or whatever. That's not what I mean. Let's start by talking about what is a niche. There's this wonderful Dr. Seuss book about niches and nutches and all of that sort of stuff. What is a niche?
A specific role within a habitat or community?
Yeah, certainly it's hard to define. Okay, what would the human niche be? That's kind of weird, right? The human niche is weird because what's happened is, where does humanity start? Humanity starts probably in the savannas of Africa, okay? Which is a different kind of. Let's think about earliest humans. What would we have been like? Would we have shaved on a regular basis? No. We'd have been pretty hairy, okay? My son is really, really, really hairy. You could put a tattoo on his back and you'd never see it. He's got that much hair on his back. I mean, he's like a gorilla. He's a hairy guy. What would we have been like?
Hunter-gatherers.
Yeah, hunter-gatherers, right? Probably not wearing any clothing. Maybe at some point to develop some protective clothing or something like that. But most indigenous peoples wear a minimal amount of clothing, right? And most indigenous peoples are living in equatorial or savanna sorts of habitats, okay? So at some point we figure out clothing, right? Probably as a protective mode. What does that enable us to do? Well, it enables you to do what the North American Indians did, for example, and that is move into places where it gets really cold, right? So they have skins and furs and things of that sort, which makes it possible to tolerate winters. Think about the Inuits, the people that came across Asia, across the Bering Strait into the Arctic, right? The fact that they had skins and things of that sort made it possible for them to survive in the Arctic. Without that, without clothing, without shoes, without leather and things of that sort, they would have never made it. Could we survive in this habitat without clothing? Probably through the summer we could, but by winter time, I think most of us would be pretty damn uncomfortable, and most of us would probably not make it, okay? We depend on clothing in order for us to make it. So what that's done is it's expanded our ability to use different habitats. A niche is, and this is a very crude definition, right? A niche is where an organism lives and what it does. Okay, where an organism lives and what it does. So, we start off as hunters-gatherers, and probably more gatherers than hunters, because we probably weren't very good at hunting until we developed tools that enabled us to do that, right? So it's where we live and what we do. Where we live has changed with our technology, clothing and things of that sort. Other organisms don't have that ability. Think, for example, of the distribution of the saguaro cactus. The saguaro cactus is this cactus that has this shape. Okay, you've seen those things if you've ever been to the Sonoran Desert. Saguaro cactus has sort of an interesting distribution. It's found only in the Sonoran Desert. You don't find it in the Mojave Desert. You don't find it in the Chihuahuan Desert. You don't find it in the Great Basin Desert. Why the hell not? Why don't you find it in any of those other deserts? It's only in the Sonoran Desert. And in fact, we refer to it as an indicator species for the Sonoran Desert. You see a saguaro cactus, you know you're in the Sonoran Desert. It's that simple. There used to be this Western, back when I was, your age, it was called the High Chaparral. It's not back before video and all that kind of stuff. It was a weekly thing on TV. Back when we only had 3 stations, ABC, NBC, and CBS, right? So that it was this weekly program, it's a Western, the High Chaparral. And you're looking at that and you're going, what the hell? This wasn't filmed in the Chaparral. This was filmed somewhere in Texas or some damn thing. Because if you knew your botany, you could look at that thing and you could tell that it was all wrong. Same thing with the television program MASH, which is about the Korean War, supposed to take place in Korea, and you're looking at the vegetation going, no, I'm pretty sure that's up around Santa Barbara. In other words, species of plants have very specific places where they occur. What is it that limits the distribution of the saguaro cactus? It's very easy. The frost line. The saguaro cactus cannot tolerate frost. In the Mojave Desert, it gets butt-biting cold. It freezes a lot in the Mojave Desert. You don't get saguaro cactus. Same is true in the Chihuahuan Desert. It can freeze. Okay? Same is true in the Great Basin. It freezes. So that's where an organism lives. It has a certain tolerance limits. And what the organism does. If you think about it, think about kangaroo rats. What do kangaroo rats do? They eat seeds. So they live in open habitats with sandy soils, and they eat seeds. Okay? What do cardinals eat? Seeds. What do goldfinches eat? Little tiny seeds. Where do you see the goldfinches during the summer? Where are they? They're on black-eyed Susans. They're on plants that have these really tiny black little seeds. They're on thistles and things of that sort. They eat these little tiny thistle seeds. They eat little tiny seeds. Okay? Cardinals eat bigger seeds. Grosbeaks eat bigger seeds still. Little tiny lizards eat little tiny bugs. Bigger lizards eat bigger bugs. Great big lizards eat plants. Okay? So a niche is where an organism lives and what it does. What I mean by tolerance limits is this. Let's look at the world's temperatures. And let's look at where people live. Okay? So, pre-tool making, any kind of tool use or anything, before humans had skins or were able to skin and tan animals or anything of that sort, where would they have lived? They would have had a tolerance limit that looked something like that. They couldn't live here, anything beyond that, because it would have been too cold. Here it's cold, and here it's hot. They couldn't live anywhere past there because it gets too hot. Okay? But by having clothing, what we've done is we've been able to do this. We have new tolerance limits right now. What defines our new tolerance limits?
Your clothing.
Yeah, how good your clothing is. Okay? I mean, if you think about, anyone ever been in the winter in Fairbanks or something like that? What's that? If you ever get the opportunity to go to the University of North Dakota in Fargo, it's kind of cool. On that campus, in the wintertime, it is brutal. I mean, you can get temperatures down to minus 20, minus 30 degrees on a regular basis, and the wind and the snow and the ice is blowing. And you've got a class in this building, and in 10 minutes you've got to be over in there in that other building. So what they do is they have tunnels that connect all the buildings. You never have to go outdoors to go from class to class. You just go down into the tunnels and go through the tunnels to get to your classes. So you don't have to go through that. That's modern technology. So suddenly we're able to make it in those places because of our ability to modify the habitat. Okay? How's about the hottest places? What happens to population density in the Mojave Desert? It goes way down. Population density in the Mojave or in the Sonoran or in the Chihuahuan Desert is low. Why? Because it's very difficult to make it. You know what it's like going... And Albuquerque doesn't even get that hot. Okay? But in Albuquerque, they have drive-through liquor stores. I know everybody has drive-through liquor stores now, but back in those days, in the 70s, that was an unusual sort of thing. There's this drive-through liquor store in Albuquerque, and this is back in the days when you'd buy a can of beer and it'd have a pull tab, not the kind of tabs now where it just folds over and you can drink it like that. These were the tabs you pulled off. So there's this liquor store, it's a drive-through liquor store, and the street in front of this, the intersection in front of this drive-through liquor store, it looked like it was chrome-plated. And what happened was people would drive through, and in Albuquerque, you could drink and drive. You just couldn't be drunk and drive, okay? You could drink and drive. So you go through there, buy your beer, grab your beer, pop the top, and flip the top out the window, and then start drinking your beer as you're driving. So the tops fall out onto the asphalt, the next car, and the asphalt is really soft because it's so hot, and the next car comes over and impales the pull tab into the asphalt. There's so many of them out there, the street is actually chrome-plated. It's aluminum, but it looks like it's chrome-plated. In Yuma, Arizona, you can walk down an asphalt street and you can leave your footprints in the asphalt as you're walking. It's that hot, okay? The asphalt is liquid. Isn't that awesome? There are parts of this planet where it gets pretty damn hot, okay? My brother lives in Long Beach, which is a suburb of Los Angeles. Over the weekend, they had 107 degrees Fahrenheit. And out there, nobody has air conditioning. Perfect. Well, because typically they don't need air conditioning, but with climate change, it's getting really damn hot out there. So he's suffering, which is fine. He needs something to keep him on the straight and narrow. All right. We can think of tolerance limits, not just in terms of temperature, but in terms of water, in terms of the availability of food, the distribution of insects for birds, for lizards, the availability of basking locations. There are some lizards which are only found in sandy habitats, other lizards which are only found in rocky habitats. The distribution of sand, the distribution of rocks forms their tolerance limits. But you have these limits, and beyond those, you can't make it anymore. Most of the organisms are abundant where conditions are ideal. And as you move away from ideal conditions, the number of those organisms decreases in both directions. That's the concept of tolerance limits. Okay, we will talk about diversity probably next time, okay? You guys, when you come back for lab, I'm going to give you back your data sheets, and I will ask you to rewrite them so that we can, not everybody will have to rewrite them, but some of you will have to rewrite them so that we can get the data. Everybody will get the points regardless. All right, enjoy the rest of your week.